So we're going to look at some practical multiple choice type synthesis problems that deal with different reactions that we've covered. I'm going to start with an E2 elimination. So we have the following substrate. And this is written in a conformation that is, well, just a little awkward, but we're going to translate it, and at the end of the day, it'll be just fine. It's not really a terse. It's not really a Newman. It's kind of an intermediate between the two. So this is our substrate, and we're going to react this with KOH. Now KOH is a strong base. This is definitely going to favor an E2 elimination. And it's in ethanol. Normally we think of an ethanol as an SN1E1 solvent, but the strength of the base overrides the fact that the solvent is polar and protic. And our answer choices for this problem are as follows. So these are the four answer choices, and before we get started, this is going to be an E2 elimination, and so A is easily eliminated because it does not yield an elimination product. Also, we are going to make a double bond between the alpha carbon and the beta carbon. We're going to remove the beta hydrogen. Remember, this is called beta elimination. Therefore, B can't be correct either, because B would be removing a hydrogen from this carbon. And it's not that that product couldn't be formed, but when we can, we'll form the most stable alkene. So the choice is really between C and D. Let's draw the Newman projection of this molecule. So just so that it's easy to follow, I'm going to draw it to the upper right-hand corner. We've got a Br coming down and to the left, a phenyl group coming down and to the right, and a methyl group that's straight up. And I think that's fairly easy to see if we look down this bond axis. So our I, if you will, is down the C alpha, C beta single bond. We also have the carbon that we can't see, and this will have a phenyl group directly to the bottom. It is anti to the methyl group, and if you look at these closely, you can see that that indeed is the case. These are anti. And then the methyl is up and to the left. The methyl and the bromine are anti, and you can see that that is the case. And of course the hydrogen is up and to the left. What's important to realize at this point is that the bromine, which I am going to make a large orange sphere, and the hydrogen on the back carbon, which I'm going to make into a blue sphere, must be anti-periplanar in the same plane with a 180-degree dihedral. In order for this to occur, I'm going to hold the front carbon steady and I'm going to rotate the back carbon by 120 degrees clockwise. What this means is that on the front carbon, the bromine is still down and to the left. And of course, all the other atomic positions are the same as well. Phenyl is down and to the right. Methyl is straight up. But on the back carbon, now the hydrogen is up and to the right. So now it is anti-periplanar to the orange sphere. This also means that the methyl group is anti to the other methyl group, and the phenyl group is anti to the other phenyl group. So when I bring the base to remove a hydrogen, this double bond goes into the plane of the screen. But if I look at the carbon-carbon double bond, the phenyl groups are oppositely oriented, like so, and the methyl groups are oppositely oriented, like so. This is clearly the E alkene, which amongst the answers that I have listed is most consistent with answer choice C being the credited response. Right now let's look at an electrophilic addition reaction, which is acid catalyzed and yields a halohydrin. So we have HCl and H2O. The first step of this mechanism is going to be the familiar proton transfer. And so the intermediate after this first step, and we want to label this first step as a proton transfer. We're going to have the tertiary carbocation as our most stable intermediate. Now, once I have this carbocation, I have a natural competition for nucleophiles. I have chloride, which is the conjugate base of HCl, and I have water. This can be very misleading if you don't realize that the stronger base will come from the weaker acid. Cl minus comes from HCl, H2O comes from hydronium. HCl has a pKa of about -7. Hydronium has a pKa of -1.73. That means the conjugate base of the weaker acid is the stronger base and the stronger nucleophile in this case, and that is water. Water will attack, and this is a nucleophilic attack, to alleviate the positive charge of the carbocation. So this is nucleophilic attack. Now in the language of Cardy, we would call this a coordination step. So I'm going to put both terms here, but the arrow pushing is one and the same. Now we're not quite done because this will still be a charged intermediate. There's really no chirality in this reaction because I can't distinguish between all these other methylene groups. So you don't have to worry about a racemate or anything like that. Now in solution, I still have chloride ion. And this is how the HCl is catalytic. I will regenerate the HCl. But notice it doesn't get the same proton that it had. The proton that HCl has comes from the water molecule, whereas the proton that HCl had became attached to this secondary carbon. So you have to be careful when you say that a catalyst doesn't participate in the reaction. The net stoichiometry doesn't change, but the hydrogen before and the hydrogen after are not the same hydrogen. This becomes particularly important in biochemistry when you're looking at enzyme catalyzed mechanisms. So our final product will be a alcohol, and it's the tertiary alcohol.
This is what he did.
So for this last reaction, we are going to simply look at the product rather than the mechanism. So let's start with the organic reactant. By the way, when you have methoxybenzene, this is called anisole. We also have a triple bond. When we have an alkyne, and to really understand the mechanism of this reaction, you have to understand the mechanism of oxymercuration, demercuration. So the reagents are HgSO4 in H2SO4. Some people will actually show water as another reactant. I would just remind you that H2SO4 is already dissolved in water, so it becomes unnecessary to list that as a reactant. You will oxidize the more internal carbonyl. Now, the problem with this reaction is you've got a choice of two that you could oxidize, and there are going to be two chemical products, two ketone products. You really want to use this reagent when you have a terminal alkyne and you don't have a terminal alkyne here. So product number one again, your chemistry is going to be to the alkyne. We have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. I can either make the carbonyl here or on the second carbon. Two products.